Hi everyone, so in this video I'm going to be comparing and contrasting electrophilic aromatic substitution or SEAr with nucleophilic aromatic substitution or SNAR. So I'm basically going to kind of define each one for you, and then we're going to do like an example of each and really understand how each one is different from the other. Okay, so we'll start with electrophilic aromatic substitution. Or SEAr. So the thing that's different about this type of reaction is that the aromatic ring that you use, most likely benzene, is going to act as your nucleophile. So basically you're going to be substituting the ring with an electrophile, right? So we've seen this many times before. So E plus is electrophile, and so your nucleophile is electron rich in this case compared to the electron deficient electrophile. So arrow flows from place of electron density to place of electron deficiency. So again, that renders the benzene ring the nucleophile. This step is going to be slow, and if you're not sure why, I'll draw the next intermediate, and that should give you a pretty good hint about why, as to why. So you'll be left with this, and you're gonna have a plus charge up here, right? Because you're using these alkene electrons to attack this electrophile. You'll have an H right there, and you'll have the electrophile, whatever it may be, attached on that carbon. And so as you can tell, this is not aromatic right here, and so it's going to be the slow step of this reaction because you're, I know you all know this, breaking aromaticity, right? Not favorable, and so this part of the reaction will be slow. All right, so the next step is going to be when you have a base, right? So we'll just do B dot to show a base. And this base needs to abstract this proton, and the electrons of which will reform the aromatic ring, the aromatic system. And so, as you could guess, this step is going to be fast, right? And why is that? Very good. I can hear all of you saying it, right? It's re-aromatization of the ring. Okay, so we're regaining aromaticity, and therefore that step is fast. And finally, our product is going to be the benzene ring with the electrophile that we substituted it with. Okay, so an example of this reaction could be the nitration of benzene. Okay, so I'll just put that there, and we'll see an example. So overall, this reaction looks like this. So this is just the general one, and I'll do the mechanism as well. So we have HNO3 and a strong acid, H2SO4 in this case. HNO3 is called nitric acid. We need it to add the nitration product on our ring, as we'll see in a moment. And then we get our benzene ring with a nitro group attached, which looks like this. And yes, I do recommend that you know the structure. It's not too important for SEAr, but when we go into SNAR in the next section of this video, you'll see exactly why we need to know the structure of this group. This is called Nitrobenzene. And you can also draw it like this. So these are equivalent structures, of course. This one, oh, you can't see that. Let me draw it up here. These are equivalent structures, right? But I do recommend that you understand that this is equivalent to this. Okay? So now we'll show you the mechanism. Okay, so in this case, we're actually going to start with our HNO3 and our strong acid. So we haven't even really touched benzene yet. So here we are. And we also have our, I'll color code this for you guys. We also have our H2SO4, which of course we know the structure of that already, right? That's old news. Okay. And so in this case now, because they're both acids, right? So now we're playing the game of which one is going to be the stronger acid that's actually going to act as the acid, right? And so in this case, we have this one right here. The nitric acid is a pKa of -1.4. And this H2SO4 has a pK of -3. And so as you can recall from Gen Chem, lower pKa means more acidic, so therefore this is going to be our stronger acid. Okay? Cool. So now what are we going to do with that information? Well, if you have the one that's going to be the stronger acid is the one that's going to be donating your proton, right? So here we have an acidic proton. So these electrons from nitric acid are going to abstract this proton, right? This is just a proton transfer. So step 1 of this mechanism is nitric acid grabs the proton off H2SO4, which is the stronger acid in this case. So it donates, of course. All right, cool. That's just a proton transfer, so not too hard, right? So the next step, so what we're left with now is right, and so now we have a water leaving group on our nitric acid, okay? So basically, as you can see, we also have these electrons here on the alkoxide oxygen, and so they're going to donate to form a double bond and subsequently kick off our very good water leaving group, right? So step 2 is alkoxide oxygen electrons donate to form a double bond and kick off our very efficient water leaving group. Okay, very good. So now, let's just make sure we have our arrows drawn in, and we also have floating around in solution our HSO4 minus counter ion, right? So make sure you can balance those charges. And we now have, of course, water that just got kicked off, right? So we also have that in solution. All right, cool. So now we're left with this structure. So we now have 2 double bondos on this nitrogen, okay? And you also have 4 bonds to nitrogen here in this frame, so we have a positive charge, okay? All right, now, since we have a positively charged nitrogen, it's more electrophilic, and this is called the nitronium ion, okay? And now we're ready for our nucleophile to enter. What's our nucleophile in this case? Good, yeah, the benzene ring, right? Because this is electrophilic aromatic substitution, and so we're going to be substituting our aromatic ring with the electrophile, in this case an NO2, okay? Cool, so step 3 is going to be the nucleophile attacks the nitrogen, right, the positively charged nitrogen, and a double bond electrons, as we're about to see, move towards O minus, right, because we're going to make an alkoxide oxygen really fast. So I'm going to make sure it's still visible in the frame, so I think if I draw it right here, you'll be able to see it. Maybe here, yeah. Here's our benzene, okay? And so we're going to just use some electrons from one of these alkenes in the pi system, and we're going to attack here, okay? And then these electrons, as we said, will form an alkoxide oxygen. Very good. Okay, so now in the next frame, what we have is this benzene ring. Okay, it's newly substituted, right? It broke aromaticity, so this step is going to be pretty slow. Okay, so because we have, so if we attached it here, let's say, right, we have these bonds still, but down here, we've got the NO2 that we just attached. I guess I'll color code it to make it a little bit easier to see. Still 4 bonds to nitrogen, so it's going to be positively charged. And we're missing something from the ring. Can you guys tell me what it is? Yeah, I can hear you all saying it, right? It's a plus charge right here, okay? And we've also got this H on this carbon, okay? So now for the next step, we need some type of base to come in and abstract this proton for us. What could it possibly be? Does anyone have any idea? Yeah, well, we've got water floating around, right? So you can use water for that too. You could also use H2SO4, right? Or HSO4 minus, excuse me. In the end, it's not going to matter because they're just going to do their thing with some more proton transfers, and you'll end up with the catalyst regenerated again, which is your strong acid, but we'll see that in a minute. And so this base is going to come in, going to take that proton, and it's going to donate those electrons back. So step 4 is going to be base, which in this case is water, abstracts proton, and I guess you can say the nucleophile rearomatizes, right? Because our nucleophile is benzene here. So I'll actually label that up here. This is your nucleophile, just in case you forget. Okay, so this step is regaining aromaticity, and therefore it's going to be, that's right, it's going to be fast. Very good, right? We know that now. And so you're left with the product that you wanted, right? So you've got your benzene ring and your NO2. I'll just draw it out. Okay, and you also have your hydronium, right, which is positively charged. But of course, as I told you before, from the previous step, from when we had HSO4 minus, right, these will have a proton transfer between them, okay, and we'll end up with H2SO4, right, so catalyst regenerated, and water. Okay, and this is your main product right here, right? We nitrated benzene, and yeah, that's it. So, and then also there's one note where you should probably know that this last step is essentially irreversible. Because how fast it is. Okay, so basically you could draw it like this for this arrow. Okay, and that's an example of electrophilic aromatic substitution. So in the next part of this video, I'll show you how this differs from nucleophilic aromatic substitution. So go ahead and click ahead to the next video.